So in this video, I want to start talking about the way in which data can be described in terms of the mean, the median, and the standard deviation. And what that does is it's going to tell us something about how the data is distributed. So to do that, let's just get to, I'm going to make my life easy here. Sorry, you might think I never use, I'm actually probably annoying you all just by my sheer inability to, because I'm in that mode. Sorry. I was in the wrong mode. Okay, so, let's talk about what these descriptive statistics would look like. So what is a descriptive statistic? Basically, it's a way that we describe the data as a whole, both numerically and graphically. So one pretty simple way to do it would be with what's called a stem and a leaf graph. And what that does is it basically starts to list all of the data in terms of the primary number, which would be the stem, and then the leaves consist of significant digits. It's really only, I almost never encounter it, and the reason why I personally almost never encounter it is because you really only can use it when the amount of data is pretty low. It's really not worth my time too much here. So if we have the number 23, then the stem is 2 and the leaf is 3. If the number is 432, then 43 is the stem and the leaf is 2. You get the idea. Basically, we have one number as our leaf, and the remainder is the stem. Not very useful unless you're dealing with, again, a rather small data set. So what we see here as an example here, they have all this data here, 33, 42, et cetera, et cetera, et cetera. Again, the stems would be the 3, the 4, and what you're starting to see there. Now, the question then would be, is why am I seeing many different leaves? Because here what we're seeing here is that there's a 42, there's a 49, and there's another 49. That would mean that there's a 53, a 55, and a 55. A 61, a 63, a 67, 68, you get the idea, hopefully. Why is it useful? Like, why would you bother through this process? And the reason why you do this process is it might help you find if there are any outliers. By that I mean, I could see here that a number like 12.3 here is very clearly an outlier because there's no even other numbers around it. Whereas 4, a lot of the data tends to congregate around this number, like in the 4 point something range. It's a quick visual way of identifying what's going on in the data, but again, only works if you have a small data set. Dude, there's no way I'm gonna watch that video. Is that guy a clown? Oh, jeez. But now I'm kind of curious. Watch it on your own time. I'm not gonna bother with it. You came here for the good stuff. Me talking. instead of a stem and leaf graph, the alternative would be a line graph, and that would be where I plot out the data and how frequent certain numbers show up. This is apparently saying that teenagers don't listen to their parents. Dude, it's not just teenagers. Even kids don't listen to their parents. Toddlers, grade school kids, they don't listen to their parents either. I don't listen to my parents all the time. So even adults don't listen to their older adult parents. But I can plot this data out, and I can see that teenagers need to be reminded around 3 times for most things. And we can see that the data starts to peak around 3 times, but also numerically we can see that that same thing is true. Bar graphs can also provide us some of the data, but it's not as visually appealing. We can kind of see some congregation here in this 13 to 25 because the bar graph itself is higher, and these others are declining. You don't tend to see this very often. Usually you would see the previous slide where you see it as a line graph instead of a bar graph. You can also have a pie chart. We can see here that the data tends to congregate around processed food. So notice that word I'm using there too again, like congregate, like where is the data sort of all leading towards, right? And then where are kind of what are people not eating? In this case, they're not eating whole grains and they're not eating their veggies, fruits, nuts, and beans. But the data seems to be congregating around processed foods and animal products, which would explain our generally poor diet. Dude, acid load to kidneys? I don't even know what that means. I don't even know what to tell you about it. I guess I don't need to tell you anything about it. I guess all we're getting here is just some other examples of where is the data congregating. This would just be saying that the richest people had the highest increase in real income. How can I see that? Because that bar chart, that bar is higher. Over here, that those who earned the most were able to reduce their taxes the most. Basically, they had the highest increase in after-tax income. I guess what we're seeing here is, I don't even know what that means. Acid load to kidneys? I don't even know what that means. So let's not worry about that. Now let's talk about some other alternative ways that we could try to describe the data. So another way we could do it is with a histogram. So what a histogram does is it has boxes that are linked to each other. And what that does is we would have a horizontal axis where we're listing one data variable, and then the vertical axis would tell us the frequency at which it's happening. So it's kind of like a stem leaf project. But what the histogram does that the stem leaf doesn't is it allows us to talk about slightly larger data sets. You have to do a lot of prep work to start to create a histogram. To create the histogram, you basically already need to know how you're splitting up the data. And that actually takes quite a bit of work, more work than I typically myself have the patience for. Let's just start to look at the data and then we'll kind of go with this here. So let's say that I was given these 100 numbers here. And these are all heights of semi-professional soccer players. So it looks like we got a lot of between 5. Shortest guy is 5 feet and the highest is 6'2", I guess. Yeah. What I would do first is I would organize that data from lowest to highest. Then what I need to do is I need to start taking from it the decimal points here. So in this case here, if we take out one decimal point here, and we wanted to start having us work with 2 decimal points, then we could subtract 0.5. What that allows us to do is it allows us to make everything basically a fraction. So 0.5, 0.05, 0.005. And if we subtract it from the smallest value, then we get something even more precise. And then we have our highest, and we could add to that the same amount, the 0.05. So that's now going to say what the lowest part and the highest point is for our histogram. So we have that precision on the tails. Then we're going to start to organize this data, the 100 points, into that endpoint and start point. Now we need to calculate how wide each bar or class is going to be within that histogram. So the way we do that is, well, basically we take our 2 endpoints, in this case the highest point, the 74.05, which we got by taking 74 plus the 0.05, the number that we picked to give us the greater level of precision, minus the lowest point, which would be the 60 minus 0.05, that would be the 59.95. And then if you wanted there to be 8 bars, then each bar itself must be made up of 1.76. We can then round that up to 2, so each interval here in this case could be 2 units wide, which then allows us in 2-point intervals then to create these intervals and then throw the data into those points, allowing us to see that the average height of a male was semi-professional soccer player basically is just about 5.5 feet tall. So it's a complicated way to construct this, which again is part of the beauty of SPSS. Because, dude, I can't tell you the last time I've had to calculate on my own a histogram. I just let SPSS do that kind of stuff for me. In fact, no, I'll do it later. I'll do it in the SPSS video. So you'll notice in these slides here, they keep doing these things with TI-84s. And for any of you who know me, you would know that I love calculators. But I'm going to skip these because we are not doing calculator work. We're not in high school. So I'm just going to skip these. You do not need to know these for the class. You're never going to be tested on it or anything like that. Okay, so besides a histogram then, alternatively, I could look at a frequency polygon. Basically, it's just like a line graph. It allows me a way to see how the data exists, again, with an x-axis and y-axis. And I'm going to connect the points, connecting the points, creating the line. And that's what we see here. So if I want to look at final test scores on a calculus exam, then what I could do here is create some ranges. So I could say how many students had an exam between 49.5 and 59.5, right, and keep going up, and then count the number of frequency that I have, and then create that range. Where now I'm talking about for students that had 49.5 to 59.5, the average between those two is 54.5. Thus my point right here. The average between 59.5 and 69.5 is 64.5, etc., etc. And you can see this right here. Again, I'm just going to take the midpoint and put my point there. Alternatively, I could create a time series graph. And again, I'm going to do all of this for you in SPSS. So in terms of how these things look and how you would have to do this after this course, don't worry about it. SPSS will do the work for you. In terms of the homework assignment will also make it a bit easier to understand because you're going to actually see the things existing there. For the time series graph, we're basically going to have a coordinate system where the horizontal axis is going to be time and the vertical axis is going to be the variable itself. So you would have seen inevitably stuff like this before, where I could look at carbon dioxide emissions, basically global warming, and I could look at it over time, and I could see that over time there was this decrease during the Great Recession. People were burning fewer fossil fuels during the large recession during the global financial crisis. Okay, so building from that, we could also then start to think about what does this look like in terms of quartiles and percentiles. What that means for us here is we're going to have to organize the data again. Organize the data from smallest to largest. And as we do that, we're then going to create the percentiles, the 90th percentile, the 10th percentile. We can make even quartiles in terms of 25th percentile, 50th percentile, 75th percentile, to give us a way to understand the distribution of the data. So, how do we do that? We can use an equation, certainly. Again, you could start to create a running list of these equations, but again, the homework assignments, if you can master those and you spend your time on those, that's going to help you on the exam because I draw the exam questions from the homework assignments. Okay, so what we could do is if I want to look for certain percentiles, I could understand those percentiles as K. And for these intervals, I could divide that either by 100 or by 4, depending on whether I'm doing percentile or quartile. N being the size of my sample. So let's look at an example here. So let's say I have all these Academy Award winners. And this is the data, and it's organized from smallest to largest. That would be a necessary step in this. So from 18 years of age to 77 years of age. And I want to do two things. I want to find the 70th percentile and the 83rd percentile. Like, what is that age that's in the 70th percentile? What is the age that's in the 83rd percentile? So, to find the 70th, both of these, by the way, are not quartiles. So I need to use that first equation for both of these. That would be the K over 100 times N plus 1. So for the 70th percentile, the K is 70. So I'd have 70 over 100. And I've got 29 individuals here, so that would be my sample size here. Well, it's actually my population. But I would have my, how many data points I have, 29 plus 1. Do the math, and I would get that the 70th percentile, that age is 21. That the 21st position is giving us the age. So then I would have to count 1, 2, etc., to get us to 64 years of age. That'd probably be the most, if you haven't, if you're in this kind of reactionary pose to just taking the number and thinking that that's the answer right there, in this case, the answer here that's given is the ordered integer. Over here, we've got the 83rd percentile, so 83rd over 100, 29 plus 1 gives us 24.9. Now, the problem with this is that 0.9 is not an integer, right? Because how can I find the 24th point, 29th position. That's what integer means position. So now I have to round it down. So I'm going to round it down from 24.9. I'm going to round that down to 24. So now I need to find the 24th position, and that's going to be 71. Then, to try to find a way to, since I'm rounding down, the 83rd percentile is basically then going to be between my 24th and my 25th integer, which would mean what's the average between 71 and 72? That would be my 71.5. I'll let you look at this here for a second, since this is another example, and then I'll explain it. I'll look at my text while you're looking at this and reading this. Although it is 1:08 in the morning, so the number of texts I receive at 1:08 in the morning is pretty small. No text messages. Okay, let's look at this data. So I've got 13 real estate prices here. I'm going to order this data from lowest to highest. That's done here already for me. Now, what I need to calculate here is the quartile range. So the quartile range, quarter 1, quarter 2, quarter 3, quarter 4. What that's going to mean here then is I'm going to use the very first equation that was over here. So k over 4, n plus 1. So in the first quarter, we have the 3.5 integer. So that's going to be rounding it down to 3. And then I'm going to take the average of the third and the fourth integer. So that would be 1, 2, 3, 4. So that's going to be here between 150, 230, 500 and 387. Now, what we're looking at here then gives us the average between those two is 308, 750. That's for quarter 1. For quarter 3, now it's 3 as k. N is now 13. Well, it's still 13. And we get our number, doing the math here, of 649. So again, if you saw there that the mistake I did here just very quickly, just when I was looking at this, was that I needed to remind myself again of that step of you have to organize the data from smallest to largest. Again, when I was just kind of quickly looking at the slide, I instead looked up at this upper 13 data points when they were not organized from smallest to largest. That was what was right here, which is why I paused for a second. Now, there's not much more I can say here. I mean, I guess really the only other thing I can say is that if we now want to take distance between if we want to find the data, the distance between quarter 1 and quarter 3 to get us some idea of the outlier, we could see that if we had a number like 5.5 million, it's pretty clear that that's an outlier because our typical range within each quartile is pretty small. Certainly not 5.5 million. Now, what if I wanted to know what the percentile was of that value that was in a data set? Then I would use this equation, and this is going to find that integer, where x now is going to be the number of the data values counting at the bottom of the list, counting up, but not counting the data point that you're actually looking at. Y here being how many of the variables, how many of the values are equal to that same value, meaning do you have any repetition? And then n being how large is the data, how many points do we have, data points do we have? Okay, so going back to the Academy Award winners, Best Actors, 18 to 77. Again, the data is organized smallest to largest. And if I want to find the percentile for the person that is 58 years of age, then I'm going to count from the bottom of the list, and we're going to see that there are 18 values that are less than 58. Let's just do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I can confirm there are in fact 18 data values. There is only one person here that is 58, so my y is going to be, my x is going to be 18, my y is going to be 1, and there are 29 individuals listed, so that's right there. So what that equals is 63.8, round up. So that would mean that 58 is in the 64th percentile. You can repeat that again, and then we can see that the age of 25 is in the 12th percentile. Again, gives me a pretty firm understanding of what the range is for the data. Now, one thing we sometimes look at here is when we look at quartiles, we might also want to look at the median. And what that might tell us is whether a person's score is, in this case what's being described here is, do I have a good score or a bad score? How do I stand relative to everyone else? That's when something like a median might be useful. Not that it's the average person, but that would mean that half as many points are above that as are below that. When we see the mean close to the median actually has an additional value. Okay, so we can see in this example here that for the 30th percentile of credit units, that students had 7 credits. What is that? What are ways that we could understand that? Well, one way to understand that would be that if the 30th percentile is 7 credits, that would mean that at that cumulative point, that 30% of the students are enrolled in either 7 credits or less. Alternatively, that would mean that 70% are in more than 7 units. But we really can't say anything yet about whether it's good or bad. All that we can say is that you lie where the other individuals are in terms of those data points. Why people are in those data points, that value judgment, we would need a much wider discussion, a much messier discussion to be able to talk about things like that. Now, one thing we can also do here is we can try to create box plots. Box plots are also sometimes also called box and whisker plots, and if you're a cat lover like myself, it's among my favorite graphs. We basically, in a box plot, we're going to create that box plot with knowledge of 5 pieces of information. The minimum value, the maximum value, where the first quartile is, where the third quartile is, and where the median is. Pretty simple stuff. But what this box plot does is it gives me, again, an idea of the range of data. And that's what we're trying to do in all of this module so far. I'm trying to get a sense of where does the data, how wide is it distributed? Looking at this example here, what if I have these data points? The lowest number is 1, so that's my 1 right there. My highest point is 11.5, that's my point right there. I would then need to calculate where is the first quartile, the third quartile, and the median. So those are things I'm going to have to calculate. Sorry, I thought they did on the next slide. We could calculate them using these equations here. Let's look at this. This would be the height of 40 students in a statistics class. So again, data is ordered from smallest to largest. Minimum value is 59. Highest value is 77. Again, calculating the first quartile, second quartile, third quartile. We're not going to do, we're not using calculators for this. You're free to use SPSS if you want, or you can just calculate it by hand. Excel also can do these things as well. So if you're on the exam, if you're in the exam or you're in the homework, you're always allowed to use SPSS. You can use another program to do some of the messy math if you want. I'm totally fine with it. There's no need to show your work or anything like that. Okay, I just want to be cognizant of your time as well and not make this too large, too long of a lecture. Let's look at how the data is distributed in terms of where is the center, where are most of the data points congregated around. There are 2 ways of understanding that. That would again be our mean or our median. Median would be in terms of quartiles again. Half of the points are, the number of points are above it, not rank ordered, but numerically ordered. Half are above it, half are below it. Mean is actually just the average of all that. And that's what's being done here. This is a fancy way of saying the average. I don't know what more you need to see from here. These sigmas aren't really telling us anything that is too interesting here, at least worth our time here. But mathematically speaking, which again I'm presuming most of you have taken college level algebra, where you would have seen this before, that the sigma means summation, that the number on top tells us how many numbers we're talking about here. The number on the bottom where it says k equals 1, that tells us where we are starting at. And we're going to add those variables all together from AK, where k is equal 1, all the way to k equals n. Add up all the terms. That's what that fancy term means. Add up all the terms. Here, I'm squaring it. So if I had 1 to 5, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Here, if j is going from 3 to 5, then it's going to be 3, 4, 5. Starting point, ending point, the general equation that I'm using here. 5 to 10, so then it's going to be 5, 6, 7, 8, 9, 10. Here, sigma I 1 to 6, so I'm going from 1 to 6 with 2. Well, there's no way in which I can now integrate I, so it's just going to be 2 plus 2 plus 2 plus 2, 6 times basically. Now the reason why we're doing that is because it allows us then to talk about what the mean is. That the mean, or the average, is basically the summation of all of the data points divided by the number of points. But you already kind of probably had a sense of that, of what an average is. This is just a fancier way of saying that same thing. And my apologies if I'm kind of dismissing this as too simple, but again, I'm hoping that most of you have an understanding of what an average means. And if you don't, you probably will know that you don't, and you'll look at these slides a little bit slower than what I'm doing here. Now, for the median, we're looking at something a bit different, because now we're looking at in terms of the percentile. And now I'm looking for the 50th percentile. This goes back to our quartile discussion. So 50th percentile divided by 100, n plus 1. Do the cross multiplication, you've got n plus 1 divided by 2. So if I had these data points, smallest to largest, the question that's asked me is to calculate the mean and the median. Try this exact same thing that's right here. Smallest, fewest number of months that a person lives with AIDS, highest number of months after taking this new antibody drug. Okay, so we already know what the equation is for the mean, basically adding up all of our terms and dividing by how many data points we have. That gets us 23.6. Then for the median, which is n plus 1 over 2, there are 40 data points plus 1 divided by 2 gives us 20.5. That would be the 20.5 integer. That'd mean the integer between the 20th and the 21st. And that would be these two 24s. So the median is 24, the mean is 23.6. The mean and the median are relatively close to each other, which we're going to see later is basically an indicator that I'm probably dealing with a normal distribution. Don't need to worry about these calculator pages because, again, we're not doing those. Mode. Yeah, it's been a long time since I've even asked anyone what the mode is to some data points. The mode would just be what data point occurs with the most frequency. And if there are two data points that occur quite frequently, then it would be called bimodal. In this case here, 72 is appearing a whole heck of a lot of times. So the mode is 72. It's occurring 5 times here. And then we just have a few other ways of describing means. Here we could do it with a frequency table. But it'd be rare that one would have to do that, so I'm just kind of skipping over it for right now. Now, I want to now understand, now that I have a sense of the middle of the data, meaning the mean and the median, now I want to understand the skewness, meaning how far spread out is it? Is it symmetrical? Or is there a long tail, meaning that either this end or this end is really, really long, and then there's a peak, and then it goes down really fast? Here, this looks pretty symmetrical. This tail is kind of like this tail, this side is kind of like this side, and then you've got your peak in the middle. This would be unimodal, as it's describing right here. You see it being bimodal when the mean and the median are very different from one another. Don't worry too. I mean, we can see the bimodal right here. Again, don't worry too much about this kind of stuff here. Okay, so let's look at this data, 4, 5, 6, 6, 6, 7, 7, 7, 7, 8. It's not symmetrical. We can see here we have all kind of a longer tail on the left-hand side and then a kind of a steep drop to the right-hand side. The mean and the median, although they look kind of close to each other, the mean and the median are actually a bit separate from each other. And the mode is obviously different from the mean and the median. The mean is less than the mean is less than the median. They're both less than the mode, so that would mean that we have skewness towards the left-hand side. We can get it the opposite way, where we're skewed towards the right-hand side. We can see that skewness if the mean is larger than the mode. So this would be basically everyone doing very poorly on an exam, right? Whereas this would be that smart people brought up the average. So when I have an exam and I give out a curve, I oftentimes tell students I want the mean to be close to the median. And again, the reason would be that you don't want the smart people ruining the curve. And over here, you don't want the dumb kids in class bringing everything down. Now, it'd be helpful to have a term to describe how this data varies. And that would be with the standard deviation. What the standard deviation tells us is it tells us what is the amount of the variation that we have. If the standard deviation is low, that would mean that the data is going to be close to the mean. Okay, so let's organize our data here again. We've got the age groups. This would be from 40. We didn't actually. So we have our data here, 41, 38, 39, 45, etc., etc. We have a mean age here. And we want to know what is the way in which the data deviates from 41.5. So to do that, we're going to need to calculate the standard deviation. And we would do that with this summation equation. Let's talk about what that does for us here. We're going to be separating data points from the mean. So in this case, I've got 41 minus 41.5, giving me negative 5. 38 minus 41.5, negative 3.5. So I would keep doing that and keep doing that, keep doing that. It's going to equal 0. And then I square my results. The reason why I'm squaring my results is to get rid of negative numbers here. And then I'm dividing by the, well, I guess it says this here. The reason why I'm squaring is to be able to talk about things in terms of their absolute value. And then what I'm doing here is I'm dividing by the number of data points that I have, which is 10. Right, from 1 to 10, giving me a variance of 8.85. Now, I need to take the square root of that. The square root of that is 2.97. That is what my standard deviation is. Yes, being able to do this mathematically, it's kind of important. But again, my hope is that you'll have a bit of an understanding of, more importantly, what standard deviation is, which is how much is the data on average deviating from the mean. And what we can see here is that the data is deviating from the mean by an average of 2.97. Yes, your TI calculator can do this, but that's not really that important. Now, once you've calculated the standard deviation, what we would do is you would basically try to look for data that's within 2 standard deviations of the mean. So that would mean that for a mean, which was 41.5, that most of our data is going to exist somewhere between 35.56 and 47.44, which is 2 standard deviations away from the mean. Where would we go with this? Like how much of the data does that give us if we take 2 standard deviations? Well, what you're aiming for here is that we're going to capture within the 90th or 95th percentile of the data. So I'm just going to skip over this just from a time perspective here, because again, I want to just get to the most important things and then kind of have the SPSS discussion, draw a little bit more of how you can make the software at least do the work for you instead of you doing it mathematically. For these exam scores from 33 to 100, what if I asked you to calculate these things? I don't want you to calculate with a calculator. What we're going to do is when I do the SPSS lecture, I'll take this data and we'll answer these things. Okay. And I'll do those as well. Okay. So that wraps up this general theoretical discussion of the mean, the median, the quartiles, the percentiles, and the standard deviation, as well as the mathematical equations that we use to generate that all. You may want to kind of highlight what the equations are, but again, for the homework assignments and the exams, you can either calculate it yourself, you can plug the data into Excel, and Excel will solve that data for you, but also SPSS will. For me, for my purposes, I care more that you understand the concept of what a standard deviation is, and you have an idea sort of how to calculate it, like longhand, mathematically, but more importantly that you could, I mean, dude, I don't calculate standard deviations by hand. The software does the work for me, and I don't think you should be held to that standard either, at least for a summer course where we're just trying to teach statistics as quickly as possible.